Okay, we are going to discuss heterocyclic chemistry right now. Heterocyclic chemistry. Okay, we will define what is an heterocyclic chemistry. So it's a branch of chemistry which actually deals with. So it's a branch of it is a branch of chemistry that deals with structure that deals with structure, reaction, properties, and synthesis of heterocyclic compounds. Heterocyclic compounds. This we call it as heterocyclic chemistry, the branch of chemistry which actually deals with the reactions, properties, structure, and synthesis. What are the ways of synthesizing heterocyclic compounds? That branch we call it as heterocyclic chemistry. Now, in these definitions, we need to define. So, heterocyclic compounds. So these are the cyclic compounds. So these are the cyclic compounds in which at least one of the constituent member of the cycle or a ring should be heteroatom. So this is, we call it as an heterocyclic compounds. So heterocyclic compounds are these are the cyclic compounds in which at least one of the constant member of their ring is replaced with an heteroatom. So that we call it as heterocyclic compounds. Now again, this definitions involves heteroatom. Now we need to define what is an heteroatom. So heteroatom, these are the non-metal containing lone pair of electrons. We call it as heteroatom. The non-metal containing lone pair of electrons. For the practical purposes, heteroatom we call it as oxygen, nitrogen, sulfur, and this also includes halogens. We call it as Cl, Br, and so on. Selenium, phosphorus, and so on. These are also termed as an heteroatom. But as far as the heterocyclic compounds is concentrated, the particle purposes oxygen, nitrogen, sulfur, these are called as heteroatom. And according to the definitions, these are the cyclic compounds. The cycle should be must. At least one of the carbon atom is replaced with an heteroatom. An example of this, we have a benzene. This is a cyclic compound containing carbon. We call it as a carbocyclic compound. Now we need to replace with oxygen. Now this is, we call it as, it's a cyclic compound. At least one of the carbon atom, constant member of the ring should be replaced with heteroatom. So it's called as heterocyclic compound. So this is, we call it as heterocyclic compound. Now according to the definitions, another example. So we have this example. Now this is oxygen, OH, OH. So this is actually a carbohydrate. This is a glucose. It's a carbohydrate. It's a glucose. Now it has a ring structure, and so it has a one atom oxygen. Now can we call it as an heterocyclic compounds? The answer is obviously no. Why? Because now according to the definitions, okay, it is a heterocyclic compound, but for the practical purposes, they are a polyhydroxyl group. It contains a polyhydroxyl group, and the properties does not resembles the property of heterocyclic. So this property seems to be carbohydrate. So they form a separate category of chemicals known as carbohydrates, because the property will actually match with the carbohydrate. They are termed as carbohydrates. And similarly, another example we have, now this is one of the ring carbon atom is replaced with oxygen, but it is not an heterocyclic, but it is a lactones. Lactones. They are termed as lactones. According to the definition, as it is a now this is anhydrides. Anhydrides, we call it as anhydrides. Another example, lactams, we call it as lactams. This is not an heterocyclic. So even though it contains an heteroatom inside the cyclic system, because the property does not match with the heterocyclic compounds. Now another example, now it is NH2. Now this is contains a lot of heteroatom nitrogen. This we call it as the name is adenine. So adenine is a part of heterocyclic system, yes, obviously, yes, but this is termed as nucleobases. This actually forms nucleobases. So the book of heterocyclic chemistry will actually deals with adenine also, but not, it does not covers almost all the, but it actually slightly touch the details of this adenine, but it is regarded as nucleobase. Now this heterocyclic compounds actually Now this heterocyclic compounds is actually classified into two categories. This classification is actually done by a scientist known as Albert. So he classified heterocyclic compounds into aliphatic heterocyclic compound, and there is aromatic heterocyclic compound. So aliphatic heterocyclic compounds, they are aliphatic heterocycles heterocyclic are the cyclic analogues. They are the cyclic analogues of amines. The cyclic analogues of amines, ether, thioether, amide, etc. So the properties are particularly influenced by the presence of strain in the ring. The property of this aliphatic heterocyclic will actually defines governed by the strain in the ring. So examples of this aliphatic heterocyclic, they are the cyclic analogues. So this is ether, cyclic analogues of ether. So cyclic analogues of amines. So this is amine. thioether. So whatever the strain that is created within the ring will actually influence the properties of the aliphatic heterocyclic system. And this compounds generally consist of 3 to 4, 3 or 4 membered, or 5 to 7 membered ring system. The 6 membered is very rare. The 6 membered ring system is very rare, but it actually attains aromatic ring. In the case of aliphatic, 3 to 4, so such as so this type of example we can give. Then next, so 3 to 4 or 7 membered or 5 to 7 membered ring system will actually make aliphatic heterocyclic system. Now another category is actually aromatic heterocyclic system. So in the case of aromatic heterocyclic system, now the aromaticity is actually categorized or characterized by alkyl. So in order to classify as aromatic, now it has to the heterocyclic system has to obey all the conditions formulated by alkyls. The first condition is actually 4n plus 2 rule, the pi electron. So 4n plus 2, it has to satisfy 4n plus 2 rule. That is the total number of pi electron within the cyclic system has to obey 4n plus 2 rule. And all the p orbitals are parallelly overlapped on the p orbital. All the p orbitals are available to make a pi bonds. They are parallelly overlap and should be planar. The ring system should be planar. So if it is satisfy all the conditions, then we can say it is an aromatic heterocyclic system. So those aromatic heterocyclic compounds will actually obey all these rules. And the property of this is actually similar to benzene. They are actually similar to benzene. An example is actually, so this is actually pyrrole. This is pyrrole. It's aromatic. It is aromatic in the sense is that now it is a planar. Now it has a pi electron. So this lone pair of electron also involved in the delocalizations. So there are 6 pi electron. So 6 pi electron, 4 into 1 plus 2. So we can take 6 pi electron in terms of 4n plus 2. So n is equal to 1. By putting n is equal to 1, we can satisfy 4n plus 2. All the p orbitals are overlapped. They are planar. So therefore it is an aromatic heterocyclic system. Now similarly we can take furan. So this is furan. Now this is thiophene. So this is thiophene. So these are the aromatic heterocyclic system. Now the study of heterocyclic compound is of great interest both from the practical approach as well as theoretical approach. So it's of great interest. The study of heterocyclic system is of great interest as theoretical point of view as well as practical point of view. So heterocyclic compounds occurs widely in nature and in a variety of non-naturally occurring compounds. So that is synthetic compounds. A large number of heterocyclic compounds are essential to life. So a large number of heterocyclic system, they are essential to life. So they are actually, so various compounds we can classified as alkalides. So alkalides contains heterocyclic moieties, and most of the antibiotics contains heterocyclic system. And amino acids, essential amino acids contains heterocyclic system. And vitamins, hormones, hemoglobin, they contain heterocyclic ring system. And a large number of synthetic drugs, will actually contains a heterocyclic ring system. A knowledge of heterocyclic chemistry is useful in the biosynthesis. It is actually useful in the biosynthesis and also drug metabolism. In order to understand the drug metabolism in the human body, drug metabolism. And another class of compounds actually contains heterocyclic moiety. They are actually nucleic acids, so they are termed as nucleobases. But in the heterocyclic chemistry, we are not going to too much deal with the nucleic acids. Only the classifications are the examples. Nucleic acids, and nucleic acids are very important in biological process of heredity and evolutions. They are very important in the hereditary, that is the genetic information, the transformations of genetic informations and evolutions. Now this heterocyclic compounds, till now there are 50 million, more than 50 million heterocyclic compounds are listed in the literature survey. More than 50 million of the heterocyclics, total number of the organic compounds. Out of the total number of organic compounds, so 50 million will be the heterocyclic compounds. So now we will take up the nomenclature of this heterocyclic system. Nomenclature. So in heterocyclic chemistry, there is a special name for each individual ring system. There is a special name for each individual ring system. Special name for each individual ring system, and there is a trivial name for each compounds. There is a trivial name for each individual compounds, and this trivial name does not give any structural informations regarding to the number of size of the ring or nature of the ring, but the trivial names they are widely used. Let's say for example, for the trivial names, so we'll take this. So the trivial name for this ring system is furan. It's furan. So similarly, the nitrogen analogs of furan, we call it as pyrrole. And this we call it as indole. And the sixth member along with the nitrogen, so this is, we call it as guanine. Another is, so this is only the position of the nitrogen is different, we call it as isoguanine. We call it as isoguanine. So these are some trivial names of the individual compounds. So in this case, we don't get any structural information or ring size, nature of the rings or nature of the heteroatom, but these trivial names are they are widely used still today. Now we need a systematic names of this heterocyclic system formulated by IUPAC. So according to, so the nomenclature is actually systemized by IUPAC system. So according to this IUPAC, there are certain rules and regulations we need to follow in order to name a given heterocyclic compounds. So here we can name from single 3 to 10 membered ring system or a bicyclic ring system and so on. So this, according to this IUPAC system, so they have given the prefixes. So we need to use for each individual ring system, we have each individual heteroatom. So we have a prefix for heteroatom. We have a prefixes. We need to use prefix. So say for example, oxygen, nitrogen, sulfur. For oxygen we need to use oxa. For nitrogen we need to use aza. For sulfur we need to use thia. oxa, aza, taya. So these are the prefixes we need to use, and then we need to use suffixes. That depends upon whether the ring system contains nitrogen or non-nitrogen. With nitrogen, without nitrogen, we need to use different suffixes. That depends upon the ring size. Ring size. Ring size. We have 3, 4, 5, 6, 7, 8. Okay, so these are the different types of ring from 3 to 4, 5, 6, 7, and we need to use suffixes. So here there are two different categories: suffix for fully saturated, fully unsaturated system. So suffixes for a unsaturated system. So in this case we have two groups with nitrogen, and here it is without nitrogen. So this is for suffix for fully saturated system. One is with nitrogen, another is without nitrogen. So with nitrogen, so we can make it two columns here. So here we have the ring size. This is okay for 3-membered ring with nitrogen. For an unsaturated system, we need to use irine, IRINE, irine. Without nitrogen, we need to use irene, here I, it is ER. For 3-membered system. For a 4-membered system, eat. Here also same. There is no difference. For a 5-membered, OLE. So here also OLE. Only the 3-membered system is different. Eat. Here is OLE. For 6-membered system, we have INE. INE. Here just IN without E. For 7-membered, epine. So here it is epine, just it's epine. We have E here without E. For 8-membered system, a sign or okine, you can take any pronounce. So this is with nitrogen, without nitrogen. Whether it's fully unsaturated system, this is for unsaturated system. Now say for example, I can take an example here. Now we have oxygen. Now this is a 3-membered ring system. So this is an unsaturated system, 3-membered unsaturated, without nitrogen. It doesn't contain nitrogen, without nitrogen. So it's a 3-membered containing, we need to use prefixes. It is oxygen fix. Okay, so prefix is oxygen, oxa, plus it is a suffix. Now without nitrogen. So it's a without nitrogen, 3-membered, without irene, IRENE. So we need to use IRENE. So we need to replace A with I. So A has to be omitted in completing the name. So we get oxyrene. So we get a name of oxyrene or oxyrene. So in this example, nitrogen. So it is a 4-membered containing nitrogen. So 4-membered means with nitrogen. So it is aza plus ETE. Here it's a 4-membered ring system, ETE. So it's a with nitrogen. So aza plus ETE. So we'll get A has to be replaced with E, azete. So this is the name, azete. Now we will complete with the ring size and suffixes for this is for unsaturated system. For saturated system, so we need to have another suffixing system. For saturated system, for saturated. So with nitrogen, again without nitrogen. So we can make two columns again. Okay. So for three-membered system with nitrogen, iridium, we call it as E R I D I N E, iridium. Now another is actually without nitrogen is irene. Without nitrogen for saturated system is irene. For four-membered ring system is etidine. Etidine. Here it is ethane. Ethane. For fifth five-membered ring system olidine. Olane. Here it is olane. So similarly for 6 and 7 membered we don't have any suffixes. For without nitrogen we have A and E. For 6 membered, for 7 membered it's epane. For 8 membered system okay. So iridium, etidine, olidine. So for the saturated system with nitrogen. So here just ethane, ethane and olane, ane, epane and okay. Examples in order to understand this for the three-membered ring system. Now this is an unsaturated system, three-membered, oxa plus suffixes with without nitrogen. This is saturated irene. So here it is oxirene, here it is oxirane, CNE, here ANE, oxirene and oxirane. Now another example, we have nitrogen H, we have oxygen. Now it's three-membered but containing two heteroatoms. Now which one we need to consider? So if it is contains more than one heteroatom, the prefixes we need to use following the order. First we need to use oxygen, then sulfur, then nitrogen. First we need to use oxa, and then thia, and then aza. So oxa, sulfur, then nitrogen. So we have this first oxygen, then nitrogen, oxa plus aza. So now it is a three-membered saturated system. So three-membered saturated system with nitrogen, iridium. Correct? It is a iridium. So we need to use iridium. And we call it as iridium. So it will be oxaziridium. Another example, sulfur. Here it is nitrogen. Now this is sulfur first, then nitrogen. The numbering should be taking place from the sulfur. If it is oxygen first, oxygen is first, then sulfur, then third nitrogen. So on the next heteroatom get the least number. If you go for here 1 2 3 4, the next heteroatom will 4. No, that's not correct. The next heteroatom should get least number. So in such a way that we need to give numbering system. Now it is thia system with nitrogen OLE. Correct? It is a OLE. Five membered with nitrogen, so it is OLE. So you will get thiazole. Should be thiazole. Lot of example. It's methyl. Now it's 1 2 3 4. So the numbering should be start from the heteroatom. So therefore it is This is, we call it as azate, 2-methyl sulfur. Now this is actually methyl. Now this is actually methyl. Now this is 1. Start from the 2, 3, 4. Now it is 2, 4 trans. They are trans each other. Trans dimethane. There are 2 methyl. Now this is sulfur unsaturated system. Now we have a sulfur. Now we have a 4-membered ring system without nitrogen saturated, so we call it as ethane. Now it should be ethane. So dimethyl thiol, so thiol, ethane plus ethane, so we'll get thietane. A should be removed. So 2,4 trans dimethyl thietane. So this is the name of that heterocyclic system. Another example, oxygen. This is nitrogen. This is H. Now this is containing 2, so 1 with the oxygen, 2, 3, 4. So it will be 1, 4 oxa first, oxa. So this is 6-membered. Now it is a 6-membered containing nitrogen. So this is for unsaturation system. 6-membered with nitrogen. So with nitrogen unsaturated INE. So INE we need to use oxa plus aza plus INE. So 1, 4 oxa, oxazine, 4 oxazine. So apart from this, there are large number of important ring systems which do not possess any systematic names. That what we said, it is a trivial name or a non-systematic name or a common name. They are used for them. So say for example, we already stated, so this is actually furan, and this is we called thiophene, and this is the 6-membered heteroatom containing ring system. We call it as pyridine. And this is pyridazine. So it contains 2 nitrogen. We call it as pyridazine. Nitrogen. Now this is, we call it as pyrine. So these are the very important in the nucleic acid chemistry. Another compound that is containing this type of structure, it's a, so this is coumarin. So another nomenclature, another system of nomenclatures that we have for a fused ring system. So for a nomenclature for the fused ring system, so first we need to use the basic structure, whether it is fused to basic structure. That is, if it is fused to benzene, we call it as benzo. So then the fusing sections we need to indicate by the letter, the side of the heterocyclic system which actually attached to another ring system, we actually labeled as a letter A, B, C by starting from the atom number 1. That is, if it is the attachment between 1 and 2, then we call it as A. If it is 2 and 3, we call it as B. If it is 3 and 4, we call it as B, C. If it is 4 and 5, call it as D. So we'll take an example in oxygen. So this is benzene, so this is benzo. So we want, so we can give number 2 3. So it is attached here, it is 2 3, it's attached to a benzene from 2 3 position. So 2 3 means B. So B. So this system we call it as furan, benzobifuran. So this is the nomenclature. Now another is actually this is sulfur. So this is 1 2 3 4 6 7. This is 8 3. So 3 4. So it will be, so 3 4 means C. So benzo C thiophene. So 1 2 3. So we have to go for 3 4, but actual numbering system goes in this direction. For in order to identify the locations or of the fusing, it was 3 4 3 after 3 4 3 4. So benzothiophene. Now another example in this category. Now it is sulfur. Now it will be 1 2 3 4 5. So we have 4 and 5. For the illustrations we are using 4 and 5 here. So 4 and 5 means benzo. So D. So this is thipene, benzo D thipene. So in a heterocyclic ring system, if it is two heteroatoms are present, of the similar identical heteroatoms are present, then the numbering should be start from the saturated one. If two identical heteroatom are present, so obviously we'll get confused. So from which heteroatom we need to start from numbering. So the numbering should be start from the saturated one. So for example, NH, this is N, this is C2H5, this is methyl. So we'll get, this is 1, this is unsaturated heteroatom, saturated heteroatom, this is 2 3 4 5. So 3 ethyl, 5 methyl, pyrazole. So this is this ring system, the trivial name is pyrazole. So another example, now it is 1 2. Now it can be named as 1 methyl indazole. 1 methyl indazole. This is saturated, this is unsaturated. This system we call it as indazole. Now another system of nomenclature, that is if an heterocyclic system containing a maximum unsaturations, in a heterocyclic system containing maximum unsaturations, if these unsaturations can be written in more than one ways, then their positions are specified by numbering those nitrogen or carbon atoms which are not multiply bonded. So what we are saying is that, so in the case of maximum unsaturations, if any one member or carbon or nitrogen or anything does not contain a pi bond, or they are saturated one. If they are saturated, so in a heterocyclic system containing maximum unsaturations, and if you find out any carbon or a nitrogen is saturated, that saturated carbon atom can be identified, specified by using, because they contain an extra hydrogen, they bear an extra hydrogens, that can be symbolized by writing italic capital of 1H, 2H and 3H, etc. We will take an example for this. This is oxygen, this is methyl. So we have this hydrogen 1 2 3 4. So fourth carbon is, it is a saturated, this is a saturated carbon. One of these two carbon is multiply bonded. Now this carbon is containing extra hydrogen. Now this we can write as 4H, because it is unsaturated carbon. 2 first we'll write 2 methyl 4H oxide ETE 4 member, doesn't contain nitrogen. So another example, now this is actually 1 2 3 4 5 6. Now this is 2H. Now we have 2H, the saturated carbon, it's a pyron. Now same will written as, if it is written here, now the number of unsaturations or number of double bonds can be rewritten in different ways. We have written in a different way. So this is 4H pyron. Now the saturated carbon can be indicated with the 4H. One, so this is numbering 2 3 4 5 6 7 member. Here it is 3H azipine. So it is an unsaturated system containing one of the carbon is saturated. So 3H azipine. Now another example, same. So this is OMe. Now here it is H. Now this is 1 2 3 4 5 6 7. Sixth carbon is unsaturated system, so we can write this is 2-methoxy 6 hydrogen zipine. So this is the name of this compound. So this is how we need to go for the naming of a heterocyclic system, whether it is saturated or unsaturated, whether it is contains oxygen, sulfur or nitrogen, whether it is contains two heteroatom or 3 heteroatom, and so on. If it is contains 3 heteroatom, we can write so it contains 3 heteroatom. So 135 triazine. So it is azine, INE, for a 6-membered system.